Okay, good morning everybody. The title of our workshop is Large-Scale Syntactic Processing Parsing the Web. So you might think it a bit odd that I started out in my first slide asking whether this is finally the right time for parsing, because of course parsing's been a central problem in NLP research for decades and has generated a huge amount of literature. But there's still this question of what is parsing good for? So our aim in this workshop has been to give NLP researchers the tools to demonstrate the usefulness of natural language parsing. And I think what unites the applications that we've got in mind, I've got some examples here, and also the applications for which parsing has been somewhat successful so far, are that they're all large scale. So an obvious example is large scale, what I'm calling intelligent information access, but I'm thinking about things like question answering, semantic search, the kind of thing that companies like PowerSet are trying to do. And also creating massive amounts of parsed data for knowledge acquisition. These are two key applications, we think. And of course, what we really want to do is exploit the large amounts of textual data that's available on the web for both of these applications. So the reason that it's finally the right time for parsing is that we've got now available robust, efficient parsers that produce fairly sophisticated linguistic representations. So a common theme running throughout our workshop is the large-scale linguistically motivated processing of web text. So this is the team who've been working on it. My name's Stephen Clark from the University of Cambridge. Two other team leaders around Cope Stake and James Curran from Sydney. And then we've got a fantastic team of students, first of all the grad students and then the undergrads. And I won't introduce them now because you'll be hearing from every grad student in the presentation who'll tell you about the work that they've done. Now you'll see from our locations that we're geographically dispersed. And in fact I did a little calculation just to try and work out how many miles we'd covered in the course of getting to this workshop. And this includes our pre-workshop meeting in California at Stanford. And I reckon it's almost 200,000 kilometres. So I don't know what the record is for the most miles travelled in the pursuit of CLSP, but I think we must be pretty close with this workshop. Okay, so I said it's about parsing the web, but in fact what we've chosen to do is focus on a subset of the web, namely the English portion of Wikipedia. And the reason we've done that, well, a number of reasons. The first is that Wikipedia, of course, is different to newspaper text. So you'll see a bit later that the parser that we're using, like most freely available parsers that people use, is based on newspaper text. So Wikipedia still provides a fairly challenging parsing problem. I mean, the text on Wikipedia is not quite as clean as newspaper text. On the other hand, it's still close enough that it's realistic. So we didn't want to jump straight into parsing blog data or Twitter feeds, for example, that sort of thing. We wanted to give ourselves a realistic problem. And the other reason for choosing Wikipedia is that there's currently a large interest in using this resource for NLP tasks, to the extent that there are even now workshops on using Wikipedia for NLP. So we've chosen a particular parser to use. I'll be saying quite a bit more about this in the next section. And this parser is based on a grammar formalism called combinatory categorical grammar. And the parser is something that I've developed with James Curran over the last 10 years or so. And it's basically a robust parser that uses a wide coverage lexicalized grammar. So this notion of lexicalization is key to our whole project, and I'll say exactly what I mean by that a bit later. So these are the research questions that we're interested in investigating. So the first one's the obvious one, which is if we take this newspaper trained parser that's got this lexicalized grammar underlying it, how does it perform on Wikipedia text? That's the first question. The second one is, can we improve the accuracy of the parser on Wikipedia, assuming that it degrades a little bit when we move from newspaper text? And in fact, one of the central questions that we ended up investigating was whether we could improve the efficiency. Because, of course, if we're interested in large-scale, web-scale tasks, we really need a very fast parser. So this became a central question that we investigated throughout the workshop. Now, we wanted to use the output of the parser for some useful tasks. So the one that we chose was disambiguation of coordination structures. The reason for this is that parsers generally perform quite poorly on coordination, and it's the kind of disambiguation problem where you can imagine that large amounts of parsed data would be very useful for improving performance. And then finally we've got what we call our blue sky task. So I think there's quite a nice range of research questions here, from fairly safe questions, if you like, to the blue sky one at the end. And this is whether we can relieve the so-called annotation bottleneck by doing a novel form of bootstrapping. So the idea is that when we move to something like Wikipedia, of course we don't want to have to create a whole new pen tree bank for Wikipedia. So we need cheap ways of creating new annotated data. That's our final research question. So the aims and goals that we set out with at the beginning, well, the first one is that we just wanted to produce a useful parser for the NLP community that everyone will use, and indeed any other community interested in parsing text, for example, the semantic web, bioinformatics, and so on. And in particular, we're interested in producing an end-to-end pipeline. So it's very useful when people take these parsers off the web that they can just feed in, say, HTML at one end and get parser representations out at the other. We also wanted to produce a parsed version of Wikipedia in multiple output formats. We thought that would be very useful for the community. But of course our main focus was really these research questions. I think these can be summarised quite nicely by saying that we wanted to investigate improving the accuracy and efficiency of a lexicalized grammar chart parser applied to non-newspaper text. And in fact what happened as the 6 weeks progressed is that we really focused on these research questions. So we're still committed to having this parser and resource available. And we did debate whether we should have it available now. It'd be quite nice to just be able to show you that you can go and download this latest version of the parser. But in fact, we decided in the end we were better off spending our time on the research questions. But just to convince you that we will have this version available, we already have this web page where you can go and download the parser. It's been up for about 2 years now, plenty of documentation. So it's just a case of us putting the new models that we've created onto this web page, and the new web parser will be available. Okay, so I've got to give an introduction to the grammar formulas. I know quite a few of you have heard this before, but it's really important because for anyone who doesn't understand CCG, you won't really be able to understand the rest of the presentation. So there are some key properties of the formalism that I have to explain. So the best way to do it is to just give a simple derivation. So here we've got a part of a sentence from Wikipedia. Now remember that one of the key properties I said of CCG, combinatory categorical grammar, is that it's a lexicalized grammar formalism. Now what that means is that for each word in a sentence we associate an elementary syntactic structure. So in the case of something like lexicalized tree adjoining grammar, it would be an elementary tree. In the case of CCG, it's a so-called lexical category. So here you can see the lexical categories under the word. So let's take a look at this one here under this transitive verb invites. So the lexical category basically encodes subcategorization information in this example. So it's the position and the type of arguments. So the way to read this slash here is that a transitive verb looks to its right, see the slash pointing to the right for a noun phrase, and when it's found it, it's looking to the left, see the slash pointing in the other direction for a noun phrase, and when it's found that, we're left with a declarative sentence. That's all the decal means on the S. Now you can see in this example that we're looking to the right for an MP, and we've got one, professional musicians, but we've got to build it. So an adjective like professional is a nominal modifier. It's a noun missing a noun to its right. So let's put these categories together. So the way we build a derivation is we combine the categories with so-called combinatory rules. So this rule is forward application. Just think of it as function application. So a nice way of thinking about it is this lexical category here is a function that we've applied to its argument. Another nice way to think about it is the categories in blue effectively cancel. So professional musicians is a noun. In fact, we're looking for a noun phrase to the right, but in our grammar, N and MP, there's not a lot of distinction, so we just have a rule that says turn any N into an MP. So now we've got that MP, so we can use function application again. So invites professional musicians is now just a verb phrase. It's a declarative sentence missing a noun phrase to its left. And we've got one of those, so we pick it up. This time with backward application because we've gone in the other direction, but it's still just function application. So that's a simple derivation in CCG. So it's quite instructive at this point, I think, to consider what we've done that's different to CFG. And in fact, if we take another example, so just a simple biomedical sentence, all I've done here is I've taken a derivation, which in CCG you normally write with the words at the top going down the page. I've just turned it upside down, so it's a binary tree. And in fact, this looks really very similar to a context-free grammar tree now. And in fact, if I change the non-terminal nodes to a VP and a V, that's exactly what I've got. So one way I like to think about this lexicalization is that we've effectively taken all the information that's encoded in the rules of a context-free grammar and pushed all that information down onto the leaves into the lexical categories. So in this example, the fact that in English we can have an S made up of an MP followed by a VP and a VP made up of a V followed by an NP, we push all that information down onto this lexical category for the transitive verb. That's what I mean by lexicalization. Now, in fact, we've got a bit more power than a context-free grammar with CCG because we have some additional combinatory rules, for example, type raising and composition, but I'm not going to go into these. These extra rules are there to, the main motivation is to recover unbounded dependencies. So I'll show you a little example later. All right, so why use this formalism? Well, there's some advantages that are often cited when talking about categorical grammar or this variant combinatory categorical grammar. So one of them you often see is that there's a so-called transparent interface between the syntax and the semantics. What that very roughly means is that it's fairly easy with this formalism to build some sort of interpretable structure like a logical form. I've already mentioned it handles unbounded dependencies particularly well. I'll show you an example in a moment of that. And the nice thing about the lexicalization is that we get a surprisingly efficient parser. So we'll see that demonstrated later. I say surprising because the fact that we've got this fairly formal grammar underlying the whole thing might make you think that the parsing will be quite slow, but it's surprisingly fast, and it's because of this lexicalization. I'll say more about that later. But the main point I want to make on this slide is that we don't really think about this workshop as being about CCG in particular. It so happens we've got this parser that is ideally suited to what we want to do. And our main point is really that other parsers based on similar formalisms like LFG, HPSG, LTAG and so on can learn from what we've learned during the workshop. And indeed, some of the questions we've investigated are really general to statistical parsing. Let me just quickly tell you about the resource that the parser is based on that we're using. It's a CCG version of Penn Tree Bank called CCG Bank. It's developed by Julia Hockenmeyer and Mark Steedman at Edinburgh. In fact, this project originally began at Edinburgh in 2000. It's one of Mark's projects. And the CCG Bank provides the grammar, which in this case is essentially the lexicon, because we've got this lexicalized grammar, plus a small number of rules that we use to combine the categories. And of course, it provides the training data for the statistical models. Now, the main point I wanted to make on this slide is that notice we've got this resource that's based on the Penn Tree Bank. So we've got a newspaper-based parser, like most parsers that are freely available.
And see, just to be clear, what the Tree Bank does for you is, even though it was created in the CFG formalism, you mentioned this idea of pushing down all the non-terminal information into the lexical thing. So that gives you your lexical tags, if you will.
Yeah.
And if you're doing L tags, these would give you elementary trees.
Yeah, that's right. So there's been a lot of work on taking the Penn Tree Bank and making it look like LTAG or CCG. Right. So the other thing that's...
But that's not the only way to get the things. You could, for example, look at a new word and say, this word I know behaves a lot like these words. So I'll give it all the tags that these words say. Yeah, and in fact, we have to do some guessing when we parse. So there's always this problem of the lexicon not being big enough. So if I come across a word I've never seen before, it's an obvious example. The other thing to say about the Penn Tree Bank is that it's important to remember that it's got all this trace information in it that something like the Collins or the Charniak parser doesn't really use. You don't see that in the output of the parser. And that trace information is very important for allowing us to recover some unbounded dependencies that I'll show you later. So here's how we parse with the formalism. It's essentially two stages. So the first stage is a tagging stage that Srinivas and Joshi, for LTAG, they introduced this idea. They called it super tagging. And they have this really nice expression, almost parsing. So the basic idea is that because there's so much information in these categories, or in elementary trees in the case of LTAG, once we've assigned the categories to the words, which is this first tagging stage, there's a lot less for the parser to do. So it's almost parsing. And what's important about this is that, of course, we can do the tagging extremely fast. So we've got a finite state super tagger that's linear time. It's just a standard maximum entropy tagger based on Ratnaparkis tagger. So we can tag incredibly fast. Okay, so the second stage I've broken up into two parts. The first one is, of course, we want to combine the categories together. This is the parsing stage. And we use a completely standard chart parsing algorithm here. CKY, it applies to CCG in a standard way. And the main point I want to make here is that in the version of the parser we started out with at the beginning of the workshop, there's no pruning at all in the chart. It's really quite surprising. So something like the Collins and the Charniak parser, you absolutely have to prune because the search space is enormous. But we've done a lot of pruning at the super tagging stage. So before the workshop, we were building the complete pack chart that contains every derivation consistent with the categories that the super tagger assigns. So here's an obvious place where we can get some efficiency speed up. And then finally, the second stage of part 2 is just to run the Viterbi algorithm using some model. So we have a conditional random field of perceptron. Yeah.
So what's the output of stage 1? Is it simply the one best tag sequence?
Oh yeah, that's an excellent question, thank you. So with the one best output, the tag is not accurate enough because it's really quite a hard problem. It's much harder than part of speech tagging. So the per word accuracy is about 92%. So what we do is we run a multi-tagger. So we just allow the tagger on certain occasions to assign more than one category when it's not sure based on the probability distribution. And we get something like 1.4 categories per word on average, and that boosts the accuracy to about 98%. So you'll hear a bit more about that later in the rest of the presentation, not my presentation. Just to give you some example of the output, we won't be seeing this again, but it's a nice example. This is the output from a tool called Boxer that was developed by Johann Boss, who's a computational semanticist. And it essentially interprets the derivations and produces this sort of first-order logical form. It's called Boxer because this is the boxed output from discourse representation theory, if you're familiar with that. But the details aren't important. This is basically just a first-order representation that you could feed to a theorem prover, for example. So just an example of the fairly sophisticated representations we can produce. Although I'm not suggesting for a minute that we've solved the formal or computational semantics problem. But we do have this first-order logical form. Now, the kind of representations we'll see more of are these grammatical relations. This is the sort of standard output of the parser, if you like. And basically, all we've got here is a dependency representation with these particular grammatical types, so things like direct object, indirect object, and so on. So I realise this is quite hard to read, so let me read you the sentence. So we've got a nice unbounded dependency in this example. That's why I wanted to use it. So it's a sentence from Wikipedia. And the sentence is, while on the lot, Hardy fell in love with Virginia Lucille Jones, a script girl, whom he married the next year. So in this line here at the bottom, we've got the word, its pos tag, and then the lexical category that was selected by the parser. Now, the reason I chose this example, let me just read part of it again. We've got Hardy fell in love with Virginia Lucille Jones, whom he married. So it's a nice object extraction example. So the object of married is Jones. And in fact, you'll see that we've got that somewhere in the output, although not quite. So you can see I've not completely cherry-picked this example because it doesn't quite do the right thing, but it's close. So in fact, we get Jones as the second object of married. And the reason for that is because the super tagger provided a ditransitive verb for married, which the parser ended up selecting. So you'll see that you can just see there are two NPs there. So in fact, the next year becomes a direct object. Where's that? There. So it doesn't quite do the right thing, but it notices...
Dative what he married?
I'm sorry?
And what he married is dative?
Right.
Yeah. Right, okay.
So you can see it recognises the object extraction, although in this case there's a big clue because we've got this word whom. So you'll see that all the action's really in this category here because whom is something that's looking to its right for a declarative sentence missing an MP to its right. So we directly encode the object extraction. So the who-whom distinction is at least useful for parsers, if not for anything else. Yeah, David.
Is there a way to somehow handle temporal adjuncts reliably? I mean, the next
Oh, it's another example of a temporal adjunct. Yeah, perhaps we should have a project on that.
Steve?
Yeah.
Yeah, how did that entry for married get into the lexicon?
Oh, yeah, that's a good question. That is a good question. It might, well, my guess is that married didn't occur enough times in the tree. Okay, so there's a little detail I've not said. So we have something called a tag dictionary following Ratner-Farkey. So if you've seen a word at least 20 times, I think is our parameter, you can only assign a category that you've seen with that word in the tree bank. For any words seen less than that, you can only assign categories that are seen with its pos tag. My guess is that married occurred less than 20 times, so it had a much bigger set to select from. But I'd have to check.
Okay, and are the probabilities at least biased toward things that you've seen with married in the tree bank? But,
Yeah.
yeah, but not enough.
Sure. Okay, so let me just say a little bit about accuracy, not too much. I just want to convince you that, of course, you want to know how well the parser performs at accuracy. We often get asked how well does it compare to the Jarniak parser and so on. I just want to say we've done a lot of tests, a recent one on the Penn tree bank where we get accuracy comparable to the Berkeley parser. But really, the Penn tree bank is not what we should be evaluating on. I think something like the grammatical relations evaluation is much better, and that's what we use. And we've got very good performance on those sorts of evaluations. Okay, so let me get on to the tasks now. So this is a description of I think it's the 5 tasks that we set ourselves. So the first one was this problem of adapting parser to Wikipedia. We just took this as an annotation task. So the first thing, we wanted some test data. So later on I'll show you how well the parser performs on Wikipedia as a test. And what we did was we took 300 sentences from Wikipedia and manually annotated them with grammatical relations. So this is really quite a significant annotation task, takes a long time. And in fact, I spent most of the workshop myself doing this annotation. We had 200 sentences to start with that had CCG dependencies. These have been annotated by Matthew Honorable from Sydney. And we also did some annotation with tags. You can do this much faster because it's just a tagging task. So we also ended up with 1,000 sentences manually corrected with POS tags and CCG lexical categories. We had a pre-processing task. So this is a really important but I think somewhat neglected task in NLP pipelines. So if you want a parser that people are going to use, it's really important they can just take it off the shelf and run it on whatever input they'd like to feed into the parser, for example, HTML. Now, in fact, what you'll hear in the next presentation from Kurt is that we ended up focusing on the sentence boundary detection task for a variety of reasons, but Kurt will tell you about that. So we looked at self-training. If you're not familiar with self-training, there's been some recent work by McCloskey, who's a student at Brown of Charniak and Johnson, who's got some very interesting results with the Charniak parser and re-ranker. So very briefly, if you take the Charniak parser, which is a generative model, and a discriminative re-ranker, parse an awful lot of data and feed that back into the generative model, for some reason that no one seems quite sure about, the performance of the parser improves, the accuracy goes up. So now, we have a two-stage parsing system as well, slightly different, but we've got the super tagger and the chart parser. So we've had this idea for a while that maybe if you parse a huge amount of data, fed it back into the super tagger, that you'd be able to improve the super tagger and therefore improve the parser. Now, in fact, what we've ended up focusing on, I think, and getting some nice results with it, is not the accuracy so much as the efficiency. So we've got this really neat idea that you can use this sort of self-train to make the parser go faster. So here's the neat idea. Remember I said that currently the way the super tagger works is that it assigns sometimes more than one category per word. And the efficiency is directly related to that. So the more categories you assign, the slower the parser goes, basically. So we want the super tagger to assign as fewer categories as possible. So here's the idea. What we can do is parse lots of data, train the super tagger on the parser output, and what we'll be doing is effectively training the super tagger to suggest categories that the parser is going to select anyway. So as long as the super tagger produces ideally the one category that the parser ends up picking, then we can't lose any accuracy, but we'll go a lot faster. That was the idea behind the efficiency self-training. And of course the advantage with self-training is we've got this effectively unlimited amount of data. So a little bit more on efficiency. We had a number of people working on this. So the first thing was just looking at the chart. So I said that currently we don't do any pruning in the chart, or at least pre-workshop. Now we do, so we've got a couple of methods. The first is to try and predict in advance which cells are unlikely to be constituents. So we've got a very nice tagging method that effectively just rules whole cells out in the chart and says, there's no way this can be a constituent. I'm not even going to bother looking at it. We also looked at beam search. A sort of flexible beam search, so Byung-Yi will talk about that later. And then we had this sort of Urowskian idea of one parse per n-gram after chatting with David. And the basic idea here is that if you come across an n-gram that you've perhaps seen lots of times before in your parser output, why bother building it? It's expensive. As long as the analysis for the n-gram is the same every time you see it, or close to the same, let's just put the analysis straight in the chart and save a bit of time. So we investigated that as well. Okay, just two left. So this was one task where we wanted to use the output of the parser. I mentioned coordination disambiguation. Of course, one of the reasons we're interested in this is that CCG has some really nice analyses of coordination. But that doesn't mean that the parser gets it right. I mean, it's really the statistical parsing model that makes the decision. So what we did was we applied a coordination re-ranker to some mbest parser output using various knowledge sources, and in particular building a distributional semantic model that was based on the output of the parser from Wikipedia. And Aurelie will talk about that later. And then just briefly, our last sort of blue sky task I talked about. Here's the basic idea. So we want cheap ways of obtaining training data. So there are various facts in Wikipedia that we think can be used to obtain high precision training data. So here's an example about Mozart being born on a particular date. So this sort of short factual snippet we think can be reliably parsed because it's quite short. We'd expect to get that right. I'd hope so. And the idea is that any other sentence containing these keywords, for example, Mozart born in 1756, those words are likely to be in the same sort of relations that we have in the output of the parser for the short snippet. So the idea is that when we see these words again in a new sentence, we can constrain that analysis based on the relations we saw in the snippet, and that can give us extra training data. And James Haggerty will tell you a lot more about that later. Okay, so the rest of the presentation, I'm going to keep going for a little bit longer, not too much longer, and I'll tell you about the accuracy results we got on Wikipedia. Kurt will talk about the pre-processing. Then we've got the large-scale tagging and self-training tasks, Jesse and Jonathan, orally on coordination, and James Haggerty on the bootstrapping. Then the break, and then the three guys working on efficiency, Byung-Yu, Yue, and Tim, and then James Curran will wrap up at the end. And we'll be showing this diagram throughout the presentation because we're here for a long time, just to keep you oriented with respect to what we're trying to do. So we've got this central component, which is the wiki parser. I'll tell you about the accuracy of that in a moment. And then the various tasks around the outside. Now you'll see that most of the arrows go in both directions. We just wanted to stress the fact that, of course, something like the efficiency feeds into the parser because it makes it faster. But a central theme throughout a lot of these tasks is this self-training idea. So the arrows go in both directions because the efficiency component uses the output of the parser. Okay, so just a few slides on this accuracy evaluation. So I mentioned that we've got these 300 sentences of Wikipedia data, and we've basically produced manual annotation in this grammatical relations form. So the way that we did that was we took the raw text and parsed it, and then we manually corrected just the CCG lexical categories, so this line down here, because we can do that fairly fast. I've done a lot of this correction. And because it's a tagging task, you can just do it in a very quickly linear way. It doesn't take an awful lot of thought to do this sort of correction. And then once you've got the lexical categories, we parse it again, but we force the parser to use the gold standard categories. And once we've done that, the grammatical relations that come out tend to be very good, not surprisingly, because we've fed in these gold standard lexical categories. So there's still some attachment decisions to be made, and the parser makes mistakes, but that annotation task is then made much easier, the correction of the GRs. So we've got this, this data set. Of course, we'll make freely available. It's a nice resource for the community, not just for us. Because let me just stress that this is meant to be formalism independent. There's no CCG in these sorts of grammatical relations. Let me just make one more point about the test. I'm going to show you a Wikipedia test in a moment, but you'll notice throughout the rest of the presentation that we also provide a lot of numbers on CCG Bank, the newspaper data. And the reason for that is that we've got this gold standard data. We wanted to use that as well. So let's see how much faster we're going on newspaper data. So you'll see numbers for CCG Bank and this Wikipedia test set. Okay, so these are the numbers we get. So this is precision and recall and F-score over those sorts of grammatical relations that I showed you on the last slide. Just to give you some idea of what we might expect with this sort of evaluation, our best number on newspaper evaluation for this sort of grammatical relations test is 83.4. Now let me just stress here that if you're familiar with the Penn Tree Bank parsing literature, and you may have seen numbers above 92, you might be thinking, oh, these look a bit low. These numbers are in no way comparable with the Parseval evaluation that people do on the Penn Tree Bank. This is a much harder evaluation, and that's why the numbers are lower. Now I've got roughly here, compares roughly because there are quite a few reasons why these two evaluations aren't completely comparable. And in fact, one of them is that in some ways we've given ourselves quite a significant advantage by creating the test data by correcting the output of the parser. Because of course we've done the correction, but still there are quite a few inherent biases in there that sort of remain in the test data. I think this is a quite interesting problem that the parsing community hasn't really thought about. So in some sense, this number should be a bit lower, but actually there's some reasons why this might be a bit lower as well. So, I mean, just to sort of finish this off, I think my informal impression, for what it's worth, having spent the last 6 weeks looking at a lot of parser output, is the parser's really doing quite well on Wikipedia text. Certainly well enough for the parser output to be useful.
Quick question
Yeah.
about comparing this with other results.
Yeah.
So the reason why you say this is a harder evaluation is because even though you're counting dependencies, you're counting label dependencies, the label set is a whole lot richer. Is that the main reason? Because otherwise I would say, why don't we just count label dependencies? That's one way of measuring.
Well, these effectively are label dependencies, but the comparison I was talking about was with the Parseval metrics, which measure how well constituents are matched.
Right, no, but I've also seen papers where people report label dependency accuracy.
Oh, yes, that's true. Yeah. Well, people tend to report unlabeled dependency, actually.
Right, no,
Well, you can measure that also.
right,
Yeah.
so, yeah, what I was thinking is whether this could be compared with other parsers by
Yeah.
saying, okay, let's do a
Right.
dependency measure
Yeah.
of parse activity.
So if you read the dependencies off the Penn tree bank trees, then you're right, this is harder because it's a richer set. And it includes things like, I should have said, this includes long-range dependencies. So it's not just the local dependencies you get in the phrase structure trees. So I think there are a whole variety of reasons why this is a bit harder.
But the GRs are still triples though, 2 lexical
Yeah.
items and 1
Yeah.
label telling how
Yeah.
to
Oh, the other really important reason is that there's a problem, which is that, of course, these GRs aren't sort of part of the internals of CCG. So we have to create a mapping that takes CCG dependencies and produces these GRs. And you lose an awful lot because of that. So the fact we're not testing on the native output. So quickly, just to finish off, one of the nice things about this GR evaluation is that we can, because that number by itself wasn't terribly useful, I don't know what you take away from that, we can look at numbers by type. So these are the three at the top are the sort of basic grammatical relations: verb, verbal argument, subject, direct object, indirect object. And these are the sort of numbers that you see for newspaper text. In fact, the indirect object one's a bit higher, precisely because for the other sort of evaluation I talked about, very often there's a difference of opinion between what's an indirect object and what's a non-clausal modifier. It's just the argument-adjunct distinction. And very often, if a test set's been produced in some other way, there might be some disagreement about that. But of course, we've produced this by creating parser output and then correcting it. So we're inherently biased towards our own view of what an indirect object is in the parser. Okay, I think I'll stop there. And now I'm going to hand over to Kurt, who's going to talk about the pre-processing.
While you get started, maybe one more quick question.
Yeah.
So if the standard parser valve, instead of just measuring labeled brackets, were to require head assignment and to measure the head assignment as part of the label, then would the two be comparative?
No. No, there are any number of reasons why these aren't comparable.
My name's Kevin Wyke, and the task I focused on during the workshop was pre-processing. And the reason why I focused on this is that users have a need for processing text at a document level, but the parser expects to have tokenized sentences. So I looked to develop a front end of the parser to tokenize and find sentence boundaries for entire documents. Excuse me. In this way, we'll have an end-to-end from processing to parsed output. So the goal is to tokenize an entire document at a time and to combine all the regular expressions so that we could tokenize very quickly. One of the main goals that we have is for speed. So we looked to boost regex and boost expressive. They had some good things that looked like they'd be promising. Support for Unicode, which we needed. C++ implementation, so we knew it would be fast. And this would allow us to have dynamic tokenization so that we could read the regular expressions in from a file, and we wouldn't have to recompile every time when we wanted to try different things. But we found that there were some problems. Boost regex was unable to determine which regular expression was matching the way we were doing it. And it didn't seem to be easily adaptable to other people's tokenization tasks. And to do proper tokenization would require many complex regular expressions. And here's an example of some of the regular expressions that we had. And the list went on quite long. So yeah, not easily adaptable for other people. And what really prevented us from using boost regex or boost expressive was the fact that we had Stack Overflow. It just wasn't scaling to what we needed. And this depended on the operating system that was being used, the length of the sentence or the document, and the length of the regular expressions, how many regular expressions we had. So I worked on this for a couple weeks, and we decided to move on to Quec. And after that, I moved on to sentence boundary detection.
So regexes are finite state, so why would you need a stack?
Why would what?
Why would you need a stack at all if they're finite state? Are you using basically a context-free interpreter to interpret them?
These are POSIX regular expressions. They are not finite state. They are not regular.
They're context sensitive. Okay.
They-
Well, why would you want those? Why wouldn't you use real regular expressions?
I believe, and correct me if I'm wrong, to keep track of details about that so we could do certain things with the tokenization when they matched. But maybe I'm
I
not.
think there's a more pragmatic question is that Perl programmers are used to having more than regular operators. So people are used to having a larger set of things these days.
Well, but it didn't work.
No, and we could well say, well, you don't get them now. So.
So I moved on to sentence boundary detection, and we can see that there's lots of things to consider. Abbreviations, initials, numbers. So yeah, there's lieutenant, American Air Force, retired. In the second sentence, we have flag, colonel, doctor, where the boundary should be after the flag. And in the third sentence, we have Mount Fuji. And that proved to be a trouble case for Punkt, and I'll talk about that in a little bit. So in order to find sentence boundaries, we look to the implementation and methodology from Kiss and Strunkt. And what I worked on is converting their Python program that's in NLTK to C++, so that we could have a faster tokenized sentence boundary detection. And we use the training data from NLTK Punkt, which is stored in a list. There's 4 different lists: a list of abbreviations, a list of collocations, a list that contains orthographic context for tokens, and frequent sentence starters. So the methodology that they have is it's a 2-stage, a type and token-based classification. So for the type, we're concerned if it looks like it's an abbreviation. And in order to be an abbreviation, it should always have a final period, 99% likely. And there leaves a little bit of chance for it not to have a period, only if that's an error. Sometimes in the text, there's errors. Abbreviations tend to be short, so if it's long, we'll penalize against that. And it's common to have internal periods. But if we have initials or ordinal numbers, we're going to override the abbreviation classification. And then we do the token-based classification. We classify as a sentence boundary or not based on these orthographic contexts, collocations of the surrounding words, and if there's frequent sentence starters that follow the period. And we'll see what those are.
Is it supposed to be a state-of-the-art boundary protector?
Yeah, I believe it's pretty state-of-the-art.
Oh, because I know, for example, that the SI has its own HMM-based sentence boundary protector.
Okay.
It does suggest
Okay, thank you. Yeah, so with the orthographic heuristic, we look at the capitalization of words to see if it has an uppercase first letter. We can call it a sentence boundary if we see that it has an uppercase first letter. We've ever seen it before with a lowercase first letter, and it never occurs with an uppercase within a sentence. It's likely not to be a sentence boundary if it starts with a lowercase first letter. It ever occurred with an uppercase first letter, and never occurs with a lowercase first letter after boundary. Otherwise, we can't say for sure, and we won't use orthographic information. Collocation and frequent sentence starters, they look to the stunning style log likelihood ratio. And for collocations, we replace the period with another word to see if 2 words have a strong bond across the period, with a period in between. And it is a collocation if we have a confidence of at least 99.5%. And for frequent sentence starters, we take sure sentence boundaries. And those things are single periods that follow words classified as non-abbreviations, and also periods that follow things that aren't initials or numbers. And we think of the frequent sentence starters as a collocation with the sure sentence boundary. So what NLTK's Punkt does is they use regular expressions to tokenize, and they miss things like Mount Fuji because the regular expression grabs that whole part and then after that moves on to the next full stop, but it doesn't consider the full stop after Fuji. What we've been doing is we zoom forward and we look for full stops, and then we look back for the token before it and forward for the next token, stopping on spaces, digits, and special characters. And these are the special characters. These characters aren't supposed to start words, and if we see it starting a word, we'll take that character as the token. Otherwise, we'll take the tokens up to that stop. And then from there, we follow the implementation of NLTK's Punkt. And what they do is they look up if the token before the boundary, or the assumed boundary, is an abbreviation, check if it's an ellipse or an initial, and then from there we make decisions. If the token is a collocation, it's not likely to be a sentence boundary. If the token is an abbreviation or ellipse and not an initial, we'll check the orthographic context to see if we can find anything from there and if we can affirm it as a sentence boundary. Otherwise, we'll check if it's capitalized and check the sentence starters. And then we'll check if it's an initial or an ordinal number, and then checking the orthographic context to see if we can deny it as a sentence boundary. So these are the results that we got testing on Wall Street Journal sections 2 to 21. There's 39,000 sentences with 63,000 full stops. And the accuracy here is how many identical full stop classifications there were out of the number of total full stops. So punct, we were able to speed up we had quite a good speed up. And it took us less than a second to go through these 39,000 sentences, 63,000 full stops. And we had an accuracy of 97% compared to Punct's 24 seconds and 95.5%. And a lot of the main differences were things like Mount Fuji, Mr. So-and-so, period, full stop, or boundary there. So they were missing a lot of those things. Otherwise, we were pretty close. And then just changing a few minor things, such as adding the month abbreviations into the list of abbreviations, got another percent accuracy. And then aligning quotation and parentheses back onto the sentence allowed us to match with even more out of the Wall Street Journal, getting us to 98.5%. So in my conclusion, I was able to implement NLTK's punct into C++ so that we could go faster. Speed up factor of almost 30 with very comparable accuracy. And now we can add this to the CNC parser pipeline, and users will be able to parse documents easier.
So I'm Jessie Rosner from Texas, and this is Jonathan Comerfeld from Sydney. And the part of the parser that we worked on was the super tagger. And the basic goal of our task was to improve the super tagging model and thereby increase parsing speed with a minimal loss of accuracy. So we have a couple questions here that we focused on. The first is we wanted to decrease the ambiguity using statistical models. So the idea here is that sometimes a super tagger can assign multiple lexical categories for a single word, and we want to minimize the number of categories it supplies to be able to increase the efficiency of the parser. We also wanted to look at whether or not we could use the parser to generate useful training data. So whenever we are switching over to a new domain, we'd like to have readily available training data. So we parsed Wikipedia, and we used that as training data for some of our tasks. The next thing we looked at was adding in some extra features for training the super tagger. So the idea here is that the more training data you have, the more useful these extra features are going to be. So when we're just training on Wall Street Journal, because of the sparsity of that data, some of these extra features are just not useful. So we wanted to see if we could add those in now that we have more training data to work with, and see if those could improve the parser. And Jonathan also looked at implementing an average perceptron model for training the super tagger, and he'll talk about that more in a little bit. So here's an example sentence for the super tagger. And so with our original model, you can see that we have multiple lexical categories being assigned for a single word. And those numbers there are probabilities. So words that the parser is not sure on, it will assign multiple categories. And the parser, or I'm sorry, words that the super tagger is not certain on, it will assign multiple lexical categories, and the parser then has to choose between those. So when we trained a new model, on the same sentence, you can see that it's now only assigning a single lexical category for each of those words. So with our new model, it's more certain about which category it should assign to those words. So I worked a lot on speeding up the training process for the super tagger. And so here's a diagram of what the original training process looked like. So we start out with our training data on a single machine. We extract features from this data, and from those features we create a single context file. So by context here we mean a single instance of training, data. And so what the context file is just those instances with all the context they occur in the training data. From that context file we then estimate the weights. And those weights are then used to construct a maximum entropy model for the super tagger. So our goal was to scale up from training on 1 million words to training on 1 billion words of Wikipedia. And so some problems that we had with our original training process for doing this are time and space issues. So the original system was limited by the RAM that was available on a single machine. And the other issue was time. So 500 training iterations over Wall Street Journal data took about 8 hours. So that's for 1 million words. So scaling up, obviously that's going to be taking a lot longer, and we wanted something that would be more feasible. So the things that we implemented were a parallelized training process using the message passing interface, or MPI, as well as the average perceptron model that John will talk about. And again, we also investigated adding in some features now that we had more data to work with. So this is one instance of our parallelization. So we first worked with parallelizing this feature extraction process. So what happens is that the training data gets distributed over multiple nodes in the cluster. Each node then extracts the features for its particular chunk of the training data. And then there's some communication there between the nodes. So we make sure that all of the same features end up on the same machine. Once each machine has extracted its features, all of those get combined into a single context file. So we have all of the context for the entire training data on a single machine. That context file then gets redistributed out, and then each machine estimates the weights for its chunk of the context file. And again, there's some communication there. And then finally, those weights are all recombined into a single maximum entropy model. So in the end, what we ended up with was a parallelized process from end to end for this training process. So we start out with the training data split up over multiple nodes. Again, each node then extracts the features for its chunk of the training data. And then we added some additional parallelization for the context file to get rid of that bottleneck there of having all of the context on a single machine. So each node took its features, created a context file for its chunk of the training data, estimated those weights. Those were recombined into a single model for the super tagger. Yeah.
And why do the extractors and these estimators communicate themselves?
So we'll actually come to the estimator section in the very next slide. And for the extraction section, it's because we want to aggregate data. And so if we have the same or very similar instance, since it's very local context in multiple situations, we want to combine those to a single instance with a count of 2. And we can't do that without communication at some point.
Are they done getting added up when you dump everything to the same file? You're saying
Well, we never dump everything to the same file in this structure. So the whole idea is that we everything is parallel. So we don't have to ever go to a single machine and have it processing everything before we get to the next stage.
Okay,
So
I thought
that's
when you combine everything, that's what happens.
well, that was how it worked in the previous version, but the final version, which you can see here, as it's entirely parallel. Yeah. So as just hinted at there, we're now going to zoom in on one particular stage, and this is the estimation process. And in the original system, it was a maximum entropy estimation or model we're building. And so for the estimation, we have a lot of communication because at every iteration, each node works on its set of contexts and then has to communicate its weights to the rest of the cluster. So as you can see, we've got every single node, each machine, communicating with every other node. Actually, using MPI, it's a little bit smarter than that, but this is the overall effect we get. And one of the issues with that is there's a lot of network usage. And why that's an issue we'll come to in a moment. So the alternative to maximum entropy models that we tried is a perceptron-based model, which is a much simpler routine and has the advantage that it takes far fewer iterations. And also the structure, as you can see, is quite different. So we start off on node 0, train on all the contexts that it has, and then it passes the weights off to the next node, which processes its contexts, and so on. It goes around the cycle, and each go around this entire cycle is one iteration. And generally, we found it took between 3 and 8 iterations to converge on a good model. So as we can see, there's far less network communication in this system. And so once we had this parallel system, we needed something to run it on. And the idea was to get as much power as we could, because we wanted to train as the largest models we could. And luckily, there are students on holiday at the moment, and so the undergraduate labs aren't in use. And so we were able to get our hands on 189 cores, which is quite a bit of computing power. And then we can do this high-performance computing on top of that. And so we were running MPI and these other processes that usually you have fast interconnects and that sort of thing. We were running that on a regular set of machines, but it gave us this great power to do these huge models. And to give you an idea of the scope of these models, we've just got a comparison of the sizes here. So the first column is our original model, just training on the Wall Street Journal. And you can see we've got about almost 1 million events, 500,000 contexts, and so on. Now we added to that 200,000 Wikipedia sentences that have been parsed by our parser. So this is not gold standard data. This is Wikipedia parsed data, which we add. And of course, once you go from 40,000 sentences to 240,000, you have an explosion in the number of contexts and events and so on, and general features, because there's just so many things that we're seeing that we wouldn't see before. And further on, we go from that, we add more features. And these are the features that were mentioned earlier. And we're trying to think if we can get more contextual information because we have many more contexts, maybe what used to be statistically insignificant features will actually be able to provide some information. So, and as you can see, we've got the number of features going up quite considerably. So what are our results? Well, so this table really captures the improvement in speed in particular. So the first column you can see there is our original system. So it's trained on the Wall Street Journal, 40,000 sentences. It's a maximum entropy model, and it's got a GIS estimation routine. And as you can see, it takes about 8 hours. Now the second column is looking at, it's the same maximum entropy model, but now we're training on an order of magnitude more text. So that amount of data has gone up 10 times, but the speed has halved. The time has halved for training. And this is because of this MPI implementation. So we can just throw more machines at the problem, and it gets much faster. The third column is this perceptron-based model. And because it has the lower network traffic, we can and with its simpler training routine, it goes even faster. And so again, we've scaled up 2.5 times from 400,000 sentences to 1 million, and yet the speed, the amount of time taken, has again decreased. So clearly there's an advantage there, and if we want to scale up to even larger data sets, you need to have this faster time if you ever want to get your model out.
Just a question. So the data set changes each time. Do you know if you ran maximum entropy and or the perceptron on the same data,
yes,
how the accuracy would differ?
Well, I can get to, so the perceptron did slightly worse than maximum entropy, yes. And actually, but having a look here though at these results in particular though, you can see our main focus is speed. The real aim, as we said at the start of this section, is to increase the speed of the overall parser without decreasing accuracy or as little as possible. And we've pretty much done that. As you can see, we've gone from around 35 sentences a second up to the high 40s, so which is a decent improvement. And we've had a slight decrease in F-score, but overall not very much. So we've got both sides of that equation. And yes, it's true. With the perceptron, you can even see here, we've got a slight decrease in performance with the perceptron. But simply it's the scaling issue. As we go to larger and larger data sets, you just can't train the other ones. So, yes. And so now I'll pass back to Jesse, who will speak about these extra features.
So we also did some experiments testing how these additional features affected the speed as well as the accuracy. And just to give you kind of an idea of what these extra features were. So the original features that were in place already before the workshop were things like looking to words or pause tags to the left and right of the current word or pause tag, as well as looking at the previously assigned super tags. So the features that we added were extending that window, so looking 3 to the left and right, as well as adding in some bigrams and trigrams of the words and pause tags. So we tested a few of these, and so we trained up 2 separate models. So the one on the left is training only on Wall Street Journal, and the one on the right testing on Wall Street Journal and 200,000 sentences of Wikipedia data. And you can see that with the when we trained only on Wall Street Journal and evaluated on Wall Street Journal, our best model got an F-score of 85.69 and ran at about 49 sentences per second. We then, training on Wikipedia, we basically didn't lose any accuracy for our best model, but we increased the speed to 66 sentences per second. So running the same experiment evaluated on Wikipedia, you can see that our best model, when trained on Wall Street Journal, got an F-score of 83.75 and ran at 36 sentences per second, whereas the one that was trained on Wikipedia had an F-score of 84.2 and ran at 59 sentences per second. So again, we met our goal of increasing the speed without losing the accuracy. So in the end, we ended up successfully using self-training to adapt to a new domain, Wikipedia, and we're able to increase the speed without losing accuracy. So just a final comparison of that baseline model with the final model that we ended up with. We haven't lost any accuracy, and we've almost doubled the speed. So at this point, we will turn over to Orly, who will talk about coordinations.
First question I have for John. If you could go back to your last slide on the message passing, the one where you had it going sequentially. Yeah, this one. So at least the way you described it to me, I don't see how the parallelism helps you, because if node 1 has to wait for the message from node 0 before it starts,
Right.
then what are you gaining by having
So in terms of speed, you're right, there's no gain here. We're actually incurring the cost of the network traffic.
Right.
The improvement is in terms of memory. So we can only store so much data on each node, and once, as you saw, the number of features is exploding, we just can't fit it on one machine. And in fact, as I tried to scale up the models, I had to expand the number of machines because we just segfault when we ran out of RAM. So it's just a matter of, and I mean, you could do other methods like writing it out to disk and reading it in blocks and things like that, but this was the architecture we went for now.
Right, because one alternative, and also, I guess, the question is how many iterations of the perceptron do you run?
So what again, this is something we only started experimenting with over the last few weeks. We would generally run 10 to 15,
right,
but dumping information at each iteration. And we found on the Penn Tree Bank, or the Wall Street Journal section, there was about the 8 iterations was where we had our best performance. Just flatline after that or get a bit worse. And then for the Wikipedia, it was much faster, around 3 to 5 iterations.
Right, because one alternative is to essentially take this, let's say you have 6 parts of your data, start each of the individual runs on its own data with the initial settings, and then do the second iteration with the update from the previous one combined with what you computed last time, and then go forward from there. And that way you'll get a slightly different algorithm.
Right, yeah.
But basically you won't have to go around the circle 8 times. You'll basically go 8 times synchronously, so you will be 8 times faster.
I mean, that was definitely worth investigating. But
in the end, I suppose you average these perceptrons, right?
Well, yeah, so it's an average perceptron system, yeah. But I mean, the model is changing at every step continuously. And I mean, you do have the issue that would give different results in some level because this one trains up and evaluates based on the current model, this sentence, whereas the other, whatever your other one has seen different data. So, I mean, yeah, it's worth investigating. But as a first step, we went straight for similar to work by Collins on the average perceptron. Yeah.
It's just that if you do it that way, you don't gain anything from the parallelism in terms of time.
Not in terms of time.
What you still do if the network if the transmission of the feature vector to the next node is faster than the disk read
Right.
time,
Yeah.
which in this case it is, even on a 100 megabit network. So it's still faster to do this than it is to read the things on
No,
disk.
I'm thinking more computationally because I guess your big bottleneck, if your big bottleneck was disk access, I would say you have to have a different strategy altogether. But I'm assuming the bottleneck is the computation.
Well, I mean, the model we showed there was training in under an hour. So, I mean, it's...
So if disk access is your problem, I would say forget parallelism of computing of the nodes. Just look into faster architecture for accessing data. That would be, in other words, I'm trying to figure out what your solution is.
Well, I mean, I suppose the thing is, this model is...
Processor, that would be text storage.
Well, I suppose the question is, I mean, this is the standard average perceptron model as proposed by Collins. And to try, what you're proposing would actually be different. You would get different results. Not necessarily worse results, but as a first step, this was the approach taken. So, and also, has the advantage, as it says up there, this is we could continue training in this way online as the system runs, and even cutting out nodes. So it's pretty flexible as well.
And a question for Jesse. So go to your results slides, for example. Anyone? Yeah, this one.
Oh.
So you guys are working on the tag.
Yes.
Yeah.
So in some sense, by reporting final parsing accuracy, you're hiding something from me, which I would like to know. Namely, remember you're saying that this, in particular, this idea about using lots of automatically parsed Wikipedia to try and figure out how to improve the tagger. This basically can be measured by saying, let's see what is the oracle accuracy of the tags the tagger puts out. In other words, you're initially putting out 1.4 tags per word on average, and you get a 98% accuracy, and now you put out 1.1 tags per word or something. Let's see if that accuracy stays at 98 or drops.
Yeah.
Or alternately, if you wanted that accuracy to remain at 98, how many tags per word you have to put out? Maybe it has to be 1.2 and not 1.1. So that would be a more direct measurement of what you're trying to optimize, and this ends up being sort of a end-to-end and extrinsic measurement rather than an intrinsic one. Do you have numbers for the intrinsic one?
Not on the slides.
Yeah.
But we do have numbers on our
Yeah,
hard drives.
Because I think if your goal is to improve the tagger, you should report them
Well,
particularly, and then say, by the way, that's just an intermediate thing. What you want to know also is how does it affect the final parser? Because if you reported only those numbers, I'd be asking you, so what does it do to the parser?
sure.
So both have value in terms of knowing what's going on. And I would be most happy to learn that 98% remained 98 and 1.4 tags per word went down to 1.1.
Right.
Or something like that.
So I think the only thing about that is that one of the things we want to do here is just predict what the parser is going to do anyway.
Right.
So in a sense, we're not necessarily comparing against a gold standard, except if you say that the parser's output is its own gold standard.
Right. No, I assume that when Steve said 98%, what he meant is or maybe I misunderstood that statement, that of the tags that the parser assigned, either a single tag or multiple tags, if you went through them and chose
Well, that would be 100% because it's got to pick one from what the super tagger actually predicts. So the 98 is against the gold standard.
No, I would say that, no, that's not quite right. I wouldn't say that's 100% because if you're given it more tags, maybe the parser would have picked a different tag than the first two you gave it. In other words, imagine not pruning in the super tagging process. Of course, that's ridiculous, there will be some pruning, but imagine being very generous in the super tagging process, of finding out what super tag the parser eventually picks, and then say, if I kept my beam to 1.4 tags per word, how many of the tags I assign are the correct tags that should be assigned?
Actually, what would be the top speed of your parser?
Well, in our experiments, it's all a question of how much accuracy you're willing to sacrifice, right? And
No, really the top speed. Assuming that you do everything right, so an Oracle experiment, would you get 100 sentences per second, 1,000 sentences per second, or?
Well, you'll see.
Okay.
We have that
Yeah.
information later.
So when the super tagger passes on more than one tag, does it also pass on the probabilities of the tags, or does the parser just assume that either of these could happen and it doesn't take those probabilities into account?
Yeah. So I think the current model doesn't take the probabilities into account. We have played around with using the probabilities. You get a bit of it. So we can move to
Okay, hi. So I'm Aurélie Abelot from the University of Cambridge, and I'll be reporting on the coordination task. So the reason why we were interested in coordination is that coordination is one of the most difficult grammatical relations to parse correctly. including in CCG formalism. So you saw in the intro slides by Steve that the parser is doing quite well on coordination, but it's definitely one of the relations that could still do with a bit of a boost in accuracy. So I've got two examples of sentences on the slides where things go wrong. So the first one is Food and Drug Administration spokesman Jeff Nesbitt said, etc. And the parser here is coordinating food and Nesbitt. So it's assuming that the food is saying something and Jeff Nesbitt is also saying something. Now, this is not completely stupid from the parser. Just think that if you replaced the word food with Smith, for instance, the correct analysis there would be to coordinate Smith and Jeff Nesbitt. So here the information that we need to have is some lexical semantics to actually decide that food and drug should be coordinated rather than food and Jeff. The second sentence is, I just don't feel that the company can really stand or would want a prolonged walkout. And here again, the parser has chosen the wrong coordination. So instead of coordinating the two words that are quite close to each other, so stand and want, it's decided to pick up the verb at the beginning of the sentence. So how do we humans resolve that kind of coordinations? There was a nice study in 2005 that showed some corpus-based evidence of parallelism in coordination. So basically, that means that we like to coordinate things that are similar. And that is similarity from the point of view of syntax. So we will say things like, he got money from his uncle and from his sister. And we like to coordinate things that are also semantically related. So you prefer to coordinate food and drug rather than food and Jeff. We also use distance features. So there was a paper in 1992 which showed that the second coordinate is usually close to the coordination. So things like the cat and, I couldn't believe my eyes, the dog were sleeping next to each other are fairly infrequent. So you usually like having the second word next to your conjunction. And in general, coordinates tend to be relatively close to each other. So in the second example that I had in my first slide, we prefer to say that the stand and want are coordinated rather than go and pick the first coordinate right at the beginning of the sentence. So this is a rough idea of what we can use as features to actually resolve those coordinations, and we decided to try and use those things in an automatic system. So I'll be presenting two systems in the course of this talk. System one is basically using the features that I just talked about. And system two is just an improved version of the first system where we added two extra features, and I'll be talking about that in more detail. So the experimental setup that we chose was to evaluate on only the conjunctions in the parses that we were getting. So the idea was for each sentence that we wanted to evaluate on, we would get the 1,000 best parses. We would calculate a baseline on the top parse for each sentence. And then we would run the system on those 1,000 best parses and then try to pick the correct coordinations out of that list. And we had a development corpus which was based on Wikipedia, so 180 short sentences. And the evaluation corpus used the combination of the CCG bank data, which has been introduced before, and Wikipedia. So we wanted to have quite a bit of training data and used section 2 to 21 of the CCG bank corpus and tested,
How many of the 300 sentences actually had conjunctions in them?
It was about 2/3, so roughly 200. And yeah, we tested on the annotated data which Steve produced in the course of the workshop. So the first system was relying on 5 different features. One was obviously the initial ranking that was produced by the parser. We had 2 distance features, as I talked about in the first few slides. There was a similarity feature, so I mean by that lexical similarity, And there we tried two different systems, one based on WordNet and one based on distributional similarity. I will say a bit more about this in a second. And we also used n-gram similarity. So n-gram similarity is just the idea that the two coordinates are more likely to be part of unigrams, bigrams, or trigrams, which are similar in terms of parts of speech. So I'll go back a bit on the similarity systems. So I won't go through the idea of the WordNet system, which was a simple edge counting system. Our distributional similarity system, those bits, has some interest because we actually used some of the data that we produced in the course of the workshop. So Jonah and Jesse produced those parses of Wikipedia, and I used a section of those to actually train the system. So that was 1.5 gigabytes worth of grammatical Wikipedia relations. And using that data, so for each pair of words that we wanted to calculate similarity on, so say you want to calculate the similarity between cat and dog, we would extract the grammatical relations for those two words, so have two lists, one for cat, one for dog, together with their pointwise mutual information. So each word had its PMI relating to each grammatical relation. So we had those two big signatures, and then we would calculate the similarity between those two lists using the lean measure, and that would give us a score. So I'll be reporting at the end all the results on the first system. I talked to you first about the features that we added for the second system. So that was relying on some observation made by people who've been working on coordination before. If you look at the literature, you will observe that very often people have worked on very specific constructs. So, for instance, Nakoff and Haast in 2005 had a paper on noun-compound coordination, so things like car and truck production. And the reason why those patterns are interesting is that they're usually quite self-contained, so you've got whole noun compounds, and you're interested in finding out the internal structure of that compound. So you know where it starts, you know where it finishes, but you want to know what's happening within that construct. And they used some paraphrasing methods, and some of the people have used things like similarity. So in that instance, we can say that car and truck are more likely to be coordinated because they're similar to each other, and car and production, for instance, are not so similar to each other. So there's been work on noun compound, there's been work on prepositional phrases, and we tried to we tried to work on two patterns, which were prepositional phrases and subject-verb constructions. So things of the type preposition, one noun phrase, coordination, second noun phrase, or two noun phrases coordinated plus a verb. So if you look at the first sentence on the screen, and you look at the last coordination, if you look just at the prepositional phrases, you've got three choices to make. So the researchers could be coordinated with the university, with Boston University. Medical schools could be coordinated with university, or the two universities could be coordinated together. So you've got to make a choice there. You know for pretty sure that the first noun phrase of those prepositional phrases are the object of the preposition. So you know that researchers is the object of, schools is the object of from, and the first university is the subject of the last of. And so what you want to do is actually find out which one of those coordinations is most likely. So the assumption is that those things are going to be coordinated unless they're very dissimilar or unless they're very far from each other. So in the first example, we of course prefer to coordinate the two universities rather than the researchers and the university, which are not so similar and which are very distant from each other. Same thing for the subject-verb construction. So now remember that we've got a list of 1,000 parses. We don't actually know which parse is correct. But we can make the assumption that we can trust the close dependencies in the returned parse. So, as I was saying earlier, we can trust that school is the object of from, for instance. And what that gives us is an indication that when you're considering that potential coordination, this is actually part of a prepositional phrase. And we've seen before that different constructs behave differently, so it's nice information to have that this coordinate is in a prepositional phrase or this coordinate is part of a subject-verb construction. So we simply added binary features, which would tell you whether you had a prepositional phrase there or some other kind of construct. And we added those features to the original 5 ones that we had. So having that list of features, we then pass them to a naive-based classifier, which will consider each potential coordination and then assign it 0, 1, or 1, depending on whether it thinks that it's correct or not. So I've got a worked example there. I realize you probably can't read that, but just to give you an idea, you've got the sentence with the POS tags at the top. The system is telling you that you've got 2 coordinations in that sentence. So one ends at the beginning of the sentence and one right at the end. So the 1,000 parses have returned for the first coordinate 6 potential coordinations and for the second 5. And the task of the classifier is just to take each one of those potential coordinations separately and then assign it a yes or no. And we, of course, take the top one. So the classifier returns a list of coordinations, which we will then evaluate on. So these are the results. So the baseline, so the initial top parse from the parser returned a net score of 71.43%. The 5-feature system using WordNet gave us a gain of about 3 points. The switch to distributional similarity still gave us a gain of 2.58, so it's a bit lower than the gain that we obtained for the WordNet system. It was actually, so on the development test sets that I worked on, the figures were actually very similar. So I would like to claim that the distributional similarity system was fairly close to what WordNet was returning. And that's fairly interesting, of course, because that means using a resource which is not manually created, so we didn't do anything to actually return those figures. And that was using quite a chunk of our Wikipedia data, which showed that, of course, it can be useful for such tasks as coordination. And adding the 2 extra features gave us, again, a little bit of gain, so 0.5 points on top of what we originally gained. So we ended up with an increase in accuracy of roughly 3.5%. So this is how things stand at the moment. So we're having that improvement on the coordination on our Wikipedia test set. The distributional similarity system performs at a level which is similar to what you could get from a human-created resource, which is good as well. The thing that we still have to do is to evaluate on the entire parse. So the figures that I'm giving you here are on coordination only. So we've improved the figure on coordination. I don't know what this choice actually means in terms of the entire parse. Now, my hope is that, of course, if you choose the correct coordination amongst those 1,000 parses, you will also return a parse that is more correct from the point of view of the other relations. So there's a hope that actually it will increase the performance of the other grammatical relations as well in the parser. But that is still to do, and we'll do that after the end of this workshop. So that is it for coordination.
For example, I want to understand your features a little bit better. Maybe you can go back to the medical schools example.
Yeah.
Right here. So maybe one.
Maybe that. Yeah. Maybe that one. Yeah.
So let's see. So there's an and.
Yeah.
And so on the right side of the and, let's say there's only one candidate. So there's not a whole lot to worry about. There's this university on the right and happens to be
Yeah.
on the left, you have candidates university from Harvard University, you have medical schools,
Yeah.
or schools, and then research.
Yeah.
These are the three candidates. So what are your features now? So if I understood right, your distance features are how far is the first university from Ann, how
Yeah.
far is schools from Ann, and how far is researchers from Ann?
Not quite, actually the opposite. So it's likely that the second coordinate will be close to the coordination.
Okay,
So I mean, in
you're
this
looking
case,
at
you don't have much.
Okay. So then in that case, you're looking at distance to university, because you also said distance between the...
Yeah, exactly.
So university and university, the second university versus schools and the second
Yeah.
university and researchers
Correct.
in the second. So these are the two distance-based
Yeah.
features. One of them happens to be redundant in this case because there aren't multiple
Sure.
text on
Yeah.
the right, but those are the two distance features.
Yeah.
Then you said the wordness similarity or whatever, semantics. So that's between researchers and universities, schools and universities.
Again, same thing, yeah.
And university and university.
Exactly, yeah.
So what are the others? So these are three features now. What are the others?
Okay, so you had also just the original ranking of the parser. So the parser is still doing quite well. So. And so do they belong to similar n-grams? So n-grams, I stopped at 3 grams. So are they similar unigrams? So basically, do they have the same part of speech? Or are they within bigrams or trigrams, which have the same part of speech? So if you remember in my third slide or so, I showed an example that we like doing things like he got money from his uncle and from his sister. So those are very similar things.
So to me, it seems that you're missing one important kind of thing, and maybe I'm just too stuck on this example, but when you have cases like this, when you have a preposition and noun coordination in there, I guess the question becomes, can you lead a university? If you can, then it could possibly coordinate with researchers,
Yeah.
otherwise it can't. Or for that matter, can the researchers be from schools and from universities? Yeah. If they can, then maybe it coordinates with that, or whatever. So what I'm thinking, for example, is that if I replace Boston University with something that does not have medical schools, then immediately you know that, it can't be medical schools. Because you can't have medical schools off the NIH.
Yeah.
Right? And so you know that it has to be further up.
Yeah, I completely agree. So
it's sort of a whole part. As soon as you have a preposition, you have not often either a whole part relationship or a physical position relationship or something. And then the feature that would give away everything would probably be if you assume that the second university coordinates with something inside the prepositional phrase, can whatever that prepositional phrase modifies, can this be decomposed as that? For example, if you wanted to expand this, you would say medical schools of Harvard University and medical schools of Boston University.
Yes, yes.
And so if Boston University can't have medical schools off,
yeah, sure. Well, what's
a proposal to coordinate the two universities?
Well, we're partly doing that in using the lexical similarity between the two universities as opposed to, the medical schools and the university. I agree with you that those are definitely features that should be included.
No, the lexical similarity is too abstract. It is out of context. I mean, in this case, there's a clear, in other words, the medical schools are of A and B.
Yeah.
And so if B doesn't have medical schools,
well, you want to get some kind of distributional information.
Or what I'm saying is that the lexical similarity has to
if
be
they're semantically similar, then surely the implication is that they will have medical school. So I agree that it's an interesting additional feature to have, but Ari's point is that you're kind of getting that through the semantic similarity feature anyway, to some extent.
Yeah, what I'm saying is you're getting an abstract semantic relationship, whereas this is a much more grounded one. It's much more...
The semantic similarity gives a backed-off version of it. It says, do they tend to occur in the same context as
yeah.
do they tend to occur in this particular context?
Yeah, I was going to say...
You might be able to use n-gram data to look at things like medical schools or medical school if you're being sophisticated of Boston University. And you might also use n-gram data to ask whether Harvard University and Boston University tend to be conjoined in other contexts. Which might be so you may not find food administration and you may not find drug administration, but you may find food and drug being conjoined as a modifier of issues or something like that.
Yeah, no, I agree. It's definitely something that would need to be added to the system.
We tend to think of conjunction as about a pair of things.
Yeah.
Like in here, Harvard and Boston. But often, actually, I believe it involves a sort of square dance with two couples. So the kind of thing here is, suppose I change this from, Dr. So-and-so led a team of researchers from Harvard and a team of losers from Hopeless University. And what I'm getting at is that it's the pair of researchers from Harvard and the losers from Hopeless. And that what you need to see is the square dance of the two couples.
Yeah.
Your two features here, I think, don't really do very well with couples. The similarities probably would work, that is, you can have at least all the gender parallels.
We just have researchers and losers and semantically similar.
Well, okay. It doesn't, you can have contrast too, right? But in order to be that different, you have to be that similar. And then Harvard and Hopeless are kind of similar too. So, coming from MIT, of course. So what I'm getting at is that the similarity features would, I think, get confused that everything's similar. And, or at least you've got one type of researcher and loser, and you've got another type of Harvard and Hopeless, and the variables all over there. And then the distance thing probably gets confused because, in fact, the distances of the couples are pretty far apart. I mean, if I replace Boston University with losers from Hopeless, then the distance is really quite far.
Well, I think the distance, so if you've got similar, let's say similar n-grams, say your two universities, your losers and your researchers, and so the distance in a way will still be the same as the distance of the heads that you're trying to coordinate. So of course the parser is making a decision, right?
Well, the head would be lead or loser. They're really far apart now, right? Because you've got the winners from Harvard being closer than the losers from Hopeless.
Wouldn't you have to change the plural on schools to a singular for your example?
Well, that's a sort of detail, but in fact not necessarily. If Harvard had several schools. If Harvard had a couple of medical schools.
But before you were, I guess somebody who was advocating a thing that we really test what the facts are, namely that Boston University doesn't have a medical school. So you have to test
and whether Hopeless has a medical school.
Right.
Right, but anyway, what I'm getting at is that I think this analysis doesn't handle the pairs, and I think that a lot of conjunctions are about pairs, especially when you get into things like gapping and sluicing. There's all these cases where you bought this from there and that from the other place.
Yeah.
So that's the way to test this. So if you go to your results, right? So you get 70% F score. Let's go to the precision part. You have 80% precision. So for the remaining 20%, are they?
You're wondering whether are they the single pairs or are they couples?
Yeah, I haven't done a detailed analysis of that. There's of course a certain number of those things which were simply, so the parser in the 1000 best parsers didn't return the correct coordination, so I just didn't have it there.
It might be the couples are rarer than the pairs.
It's definitely something to look at. Yeah. Thanks.
We've just got one more presentation from the room.
Thank you. So, as it shows up there, and as Steve mentioned at the start, I'm working on this factual bootstrapping idea. And as Jesse and Jonathan were talking about self-training on parser output, what we'd ideally like to do is kind of take the parser output and use the parser to improve the output, to in effect get additional reliable data, reliable training data for free. And the basics of this idea is because we assume that the same idea is expressed many, many times, particularly on the internet. We can get a lot of web text that's saying essentially the same thing in different ways. So how can we exploit this information? Because of course, if we have a whole lot of sentences that are saying much the same thing, we can do something with it. Well, the most obvious thing to do is to take an easy sentence like Soderbergh directed the movie Traffic. And then we know, presumably, that Soderbergh is someone who would direct the movie Traffic. And then we can parse a slightly harder sentence. And this may seem rather short, but it's partly because I can fit the example on the next slide, and also partly because the parser still gets it wrong, since out of sight is clearly an unusual kind of construction, and perhaps you'd want to do some kind of phrase or chunk identification first. But as it is, this is something the parser gets wrong, but of course if we know that Soderberg directed traffic, it can get the coordination right, this sort of thing Ollie was just talking about. So the idea is we find these constraints from a simple sentence. We look at words we're interested in this case Soderberg and traffic, and see how they're connected. And we take those set of grammatical relations, and then when we're parsing a larger sentence with those words involved, in this case all three words, Soderberg directed and traffic, adding on directed since that was the word that connected those two, we say that sentence has to obey those particular constraints. So in this case with Soderberg directed out of sight and traffic, what you see is the red lines were the initial parse, and those are just the dependencies, the grammatical relations that Steve introduced you at the start, and the green lines are the supposedly corrected parse. Now, firstly you'll note that it's worked out that traffic should be the d-obj of directed. This is the constraint we put on it. And happily that's also fixed up the sight fact. Sight is also the object of directed. Unfortunately, it's still making a bit of a mess of out of sight because, well, that's a hard kind of thing to parse, and out is still connected to directed here. But it's got substantially better than it was originally. And this is really the idea. We're not hoping to sort of fix it entirely, but we're hoping to give the parser extra data to make it at least a little bit better to do this, and to do it automatically, to do it with sort of no cost at all. So what I did with all this is I augmented the original training data. And the basics of the idea was that, well, you want to choose things that are related in fairly consistent ways. So in this case, in the example, we can say that Soderberg and traffic are going to be related in a consistent way. That doesn't, of course, mean that Soderberg was always directing traffic. Maybe it was Soderberg's film traffic or some other kind of connection. But if we have enough data, we can generalize across that and we can say, well, hey, these are all the ways that this kind of director-film relation is likely to be encoded. Of course, for some kinds of relations, like dog and cat, well, who knows really what would be going on in a sentence with dog and cat. We don't have a sort of fact about them. We don't think, well, hey, that's going to be consistent. So we want some way to choose the kinds of relations that we think, well, hey, we're really only expressing one idea here. We're not going to see something completely out of the box with these particular words. And the question, of course, is, well, how do we get thousands and thousands of relations that are related in the same way? And as always, really, the answer is the web and Wikipedia and that sort of thing. In this case, what we were using, well, what we looked at using here was something called Freebase, which you may or may not be familiar with. Essentially, it's an enormous database extracted from a lot of internet resources, primarily Wikipedia, but also I think things like MusicBrainz or IMDb, that sort of thing. So you can just make queries. In this case, queries like, well, what are all directors and films they directed? What are all inventors and their inventions? And of course, when you do something like that, you can not only look for all instances of Soderberg and film and how Soderberg and traffic and how they're connected, but you can also look for Tarantino and Pulp Fiction. And you can say, well, here are the relations that are consistent across these two particular, classes. Consistent within this one particular class. And we can use the sort of the different entities to support each other. And we can use things with, well, maybe we've only got one or two sentences about some very small art house film, but we can still use those sentences because we have all this information about how films and directors are generally connected. So here's a little diagram of how the whole process fitted together on the last run, which I'm going to present. We extracted 247 classes from Freebase. Now this is not queries, this is actually how many director, film, inventor, invention, that sort of thing were connected. Then we use those to find sentences on the web. We got around 2 million of those. Now that's after looking at a lot more because this is a fairly restrictive process. We're taking sentences, firstly, that obey, well, for one, things that in this kind of scale that we just extracted from the abstracts that Yahoo Boss returned. Secondly, we took sentences which fitted our constraints. They weren't ridiculously long. They looked very reasonable in that they didn't have strange mess in them, ellipses, strange characters, and also that they didn't have things like who and he, she, it, because of course if you have something like Soderbergh was born in, I don't know, and directed the film, and he directed the film Traffic, the grammatical relations will end up saying he directed Traffic. And when we try and apply that constraint, it will make a horrible mess of the sentence. So these are a restricted subset of sentences. We still had quite a lot of them. Of those sentences, we took the straightforward ones. The ones we felt, hey, we can definitely parse this thing. This is a simple sentence. So this was just, at the moment, was some sort of simple hard constraints about, well, how many verbs are in the sentence? Does it look like it's, well, is it a fairly short sentence? That sort of thing. And then we parsed all of the sentences we'd collected using those constraints that we'd extracted. So of those, we got about 240,000 sentences that were successfully constrained, in that we could say, well, those sentences obeyed the constraints, and about 43,000 of those where applying the constraints actually changed the output of the parser. So hopefully corrected it. So here's a discussion of the sort of experiments we ran. This is the last run. What we did was we took a subset of CCG bank, which is, of course, around 40,000 sentences, since it's an adaptation of the Penn tree bank. And we did this to simulate bootstrapping off a relatively small amount of data. And we generated a few different models. So there are sort of a few different baselines that you're interested in this kind of case. Your initial model, the thing you're trying to bootstrap off, but you also want to see what the effective self-training is, because as Jesse and Jono said, or simple self-training, because as Jesse and Jono said, that you can sometimes get an accuracy improvement simply from that. So we looked at self-training on the wiki and on random wiki data, random web data, and data that was actually used for constraining, because of course this is a kind of skewed subset of all the data out there, and there's a bit of concern that, well, we might be teaching our parser to parse really well these sentences about directors and people's birthdays, but that might not be generally applicable. And then we looked at constraining it in different ways. So as I was discussing, there are two real things that are happening here. Either it obeyed the constraints anyway, we didn't have to change the parse, or it did have to change the parse. So we want to look at the overall case, the changes where it fixes it, the changes where the cases where it wasn't changed at all. And then finally, because of the concern that, well, you know, sometimes we might be fixing it and, well, we shouldn't really be fixing it. We've made some mistake about how these words are connected. We looked at those sentences which had the least probability change, even though they were changed. So, of course, if the parser had to do something very strange to parse that particular sentence, you would expect it to be much more improbable than the original sentence that was produced. And perhaps we don't want to look at those cases. We want to look at the cases where there were small adjustments. So what we'll look at next is the actual results. And as this is on the Wall Street Journal and CCG Bank. And initial is the baseline, the model we started at. The next three are the sort of different kinds of baseline models. And the final four are those different kinds of constrained models that I talked about. And unfortunately, you'll see here that, well, nothing terribly interesting happened, even when we got up to triple the data. The F scores were, you know, all around 75, 76%. And unfortunately, the more interesting things we did, the F score actually got slightly worse. Given the variation across experiments, it's not exactly clear, unfortunately, how significant this is. I mean, is it that we're actually generating too many bad sentences and so destroying it, or is it just some kind of natural variation? But one particularly worrying result is that this ordered model, which is the final one where we were selecting things that had limited change, and then training on exactly the same data that used. So this used data is the same data as the ordered model. It's not equivalent to any of these. And in other words, training on all the sentences we think were wrong versus training on all the sentences we think were right, training on the sentences that were wrong performed better. So clearly something is going wrong. And what we need to work out, I guess, is to what extent it's that, well, we're generating too many wrong sentences, or maybe we're not generating that many wrong sentences, but the wrong sentences are really bad. So I think different kinds of experiments need to be run. What you'll see in the next slide is...
Go back, let me ask you a question though. So let me start the initial, I guess that's some sort of baseline you have without doing any of this?
Yeah, so what happens is we train an initial model on this 7,500 sentences, and then we use that model to parse other sentences. So first to parse the sentences to extract the constraints, the simple ones, and then to using those constraints to parse all the sentences. So it's sort of the fundamental thing that's used to generate all these other numbers. And this is why these numbers are quite a bit lower than the other numbers you've seen, because it's a subset of CCG bank.
A diagnostic or an initial statistic I'd like to see is, in the baseline parser that you have, how many of them contain a parsing error of the kind you're trying to fix?
Well,
that's number one. Second, of those errors, how many are covered by your simple sentences so that constraining them might actually have some hope?
So we're trying to fix all errors, okay? Because what we're trying to do is augment the original training data.
Right.
We're hoping that, well, if we fix these things, like that example with Soderbergh-directed traffic, well, hey, we're getting the whole coordination there right and fixing up a couple of different relations in the sentence. And we're hoping that, well, hey, maybe it'll fix any kind of error in the parser. Essentially, it's additional training data. So there's no sort of particular subset of errors that we can say, well, we're doing better on these ones or not doing better on these ones. The point is to improve the whole process. Is that answering your question at all, or maybe say it again? And I'll...
Because I'm thinking this test set, by the way, is the Wall Street Journal test, right?
Yeah, you'll see the Wikipedia one on the next slide.
So what I'm thinking is that maybe the reason why things get worse is because there is nothing you can pick up from all these other
Yeah, so it may be that
fix them.
we're learning a whole lot about a whole lot of lexical information and super tags that just really aren't useful for the Wall Street Journal. Unfortunately, the same thing happens with Wikipedia. So I mean, I guess it is, and this is something I'll talk about in the conclusion, it is possible that we're improving the parsing on, film director sentences or people who invent things. But the hope is that we could use that to generally improve results. This may not be true, and maybe we should be doing a subset of these kind of relations, but whether that's useful or not is sort of more debatable. Whereas if we could show improving on the general parsing task, that's clearly a very interesting result. So I guess we went for the bigger result first, and maybe that was slightly too ambitious. But as Steve said, it's the blue sky project. Is that, yeah?
Do you do gradual increase in your training data?
So you're talking about this double and triple the data.
The double is not really gradual.
So, I mean, this is building on work that James Curran and one of his ordnance students did last year. And in that set of experiments, they weren't using freebase, they were sort of manually selecting queries. And they found that, in general, there just wasn't enough data to affect the parsing outcomes. It didn't change what the parser was doing. And in my initial experiments, I started using smaller bits of data and more limited sets of queries, which I could be more sure were doing the correct thing. And unfortunately, I still didn't, see any improvement. So it was sort of a theory, well, hey, maybe we just really don't have enough data. Maybe this thing needs to be a much larger scale. So also, the problem is, the reason why I can't show you a graph of this is that all this takes quite a lot of time. I mean, for every time, for all of the, 16 models here, there's, I have to train the pos tagger, the super tagger, and then train the parser on a cluster. And it would be impractical to actually have, a nice graph with 10 points on it or something like that.
There's many bootstrapping experiments, especially, for example, Yaros's algorithm, which was one of the first bootstrapping algorithms, actually performed this in a very gradual way. So,
yeah, I mean, I guess the problem is it's not really like classical bootstrapping. And it would be far too, time intensive to actually say, well, now we'll parse five word sentences and try and improve our sort of 6 to 10 word sentence performance and that sort of thing. So, I mean, I guess the hope is that we could do it in a simple way. Maybe not so. Maybe it just needs more refinement. So anyway, as I was talking about, the Wikipedia results are, if anything, slightly worse than the Wall Street Journal result. There are some slightly interesting things happening with, for instance, in the triple the data, with the ones that we're not even modifying. You can see the ones that we're not modifying at all. In other words, if we're just using the constraints as a kind of verify that this is okay data to feed to the parser, then that's substantially outperforming the fixed model. That's kind of encouraging because it says that, well, hey, we're probably damaging performance because we're skewing the data, right? And that's why we're dropping from 75.7 to 75.0. But our constraints are doing something vaguely interesting because, well, hey, 75% is better than just selecting the bad sentences or better than selecting, the 74.76 of the constrained data. So maybe it is just that our errors are really bad, and that the fact that we're pushing the parser in the right way sometimes is outweighed by the fact that, well, other times the errors are really messing it up. So really, as I've been stressing, this is a project that we just need to work more on. It's an idea that could potentially improve parsing performance quite a lot, because you can get an enormous amount of this data, particularly from Freebase. The 247 relations I extracted were certainly only a subset of the potentially millions of relations that you could take from that. And there are all sorts of places where we're thinking, well, hey, maybe if we did this, it would get better. And you can even view this as the kind of task that you might, use a computer to select a large range of sentences, and then use a human to really easily filter the remaining sentences to improve the sentences that are selected. So much less expensive than getting Steve or someone to annotate all the grammatical relations. And we think there are issues with skewed data. The kinds of sentences we select because of this process means the parser learns a lot about certain kinds of sentences and not about others. It might be nice to have selected test sets to get some kind of sense of, well, hey, is this doing something useful at all or not? And we do have an idea of that, because we've looked at the actual output and seen, well, a number of sentences are being corrected, a number of sentences are being messed up. The hope was that the corrected ones would outweigh the messed up ones. It's probably not true. And then, of course, there is the idea that, well, you might want to do this in a domain-specific way, or extend this kind of idea, I think, as Dikang suggested in an early talk, that, well, that rather than building this thing and then using the training data, you might want to use this kind of approach just to find, for any particular sentence you had to parse, in a very different kind of way, finding probabilities rather than applying these relatively hard constraints. So basically, there's a lot more to do. This is the time when we plan to have a break, so I'll leave it at that for now.